Hello everyone. Let me introduce myself. My name is Honesto Pardede, and I am here to presentate about metallurgy on mechanical properties and strengthening mechanisms. I'm from Teknik Fakulty, Universitas Udayana, and here I got the reference from Metallurgy for the non-metallurgists, second edition, edited by Arthur C. Reardon. For the content, we got 3.1 mechanical properties and 3.2 strengthening mechanisms. Let's jump on the first one. We got mechanical properties. Mechanical properties is when a force or a combination of forces are applied to a material. The material responds by deforming or straining, often in a complex manner. For example, when a bungee jumper hops off a platform, the bungee cord stretches dramatically, and at the same time its cross-sectional area decreases. Under normal circumstances, the bungee cord safely prevents the jumper from hitting the ground below, while this example describes a type of deformation that is readily visible. Often deformation of this type cannot be observed this easily, but it does still take place. For example, a weight hung from the end of a steel wire will cause the wire to stretch and its cross-sectional area to decrease. But the amount of deformation is not readily observed without performing careful measurement of the length and diameter of the wire loaded. Mechanical properties describe the relationship between the stresses acting on a material and the resulting deformation the material undergoes as a result of these applied stresses. The concept of stress in its most general form is force or load divided by the area over which it acts. Different types of tests with use and applied force can be employed to measure other mechanical properties as well. Additional examples of such properties include the elastic modulus, hardness, fatigue resistance, and fracture toughness. These are described subsequently in more details, as we can see in my presentation. We got hardness, elasticity, ultimate strength, fatigue, impact toughness, fracture toughness, high temperature resistance, damping properties, and wear resistant properties. As we can see, and some typical room temperature mechanical properties of selected metal are listed in table 3.1. At figure 3.1, we can see a standard tensile test specimen used to measure the mechanical properties of metallic materials. As you can see the figure here, reduced section, the gauge length and elongation or stretch. As you can see the stretch. And figure 3.2, engineering stress strain curve. The intersection of the dust line with the stress strain curve determines the offset yield strength. The offset yield strength when the necking begins is the upwards uniform strain. Tensile strength and fracture stress is when the strain can't go back to its form before the fracture begin. And the elasticity. In the elastic region of the engineering strain curve in figure 3.2, stress is linearly proportional to strain. This region is the straight line that can be seen on the left-hand side of the strain diagram. When the crystal is stressed by an internal or external load, the lattice strain in response to the applied stress through the relative movement of the atoms. When the load is removed, the crystal or object will return to its original size. And shape, provided that all the bonds between the atoms in the crystalline lattice are not stretched too far. It means it can return to its original size without fracture. This law of proportionality is called Hooke's law. after Robert Hooke. The linear relationship between applied stress and elastic strain result in a physical property called the modulus of elasticity of the material. The modulus obtained under axial tension or compression loading is called Young's modulus, and it's represented by E. I get the table also, the table from the table that we can see some typical room temperature mechanical properties, yeah. And then mechanical properties, such a figure 3.3, the general comparison of engineering stress strain curve of figure A, various steels at room temperature, and B, gray cast iron at different classes strength levels. Modulus for steel is roughly constant at different level of strengths, but the modulus of gray iron is more variable due to softness and flake or lamellar morphology or graphite in gray irons. It's the plasticity, the point at which plastic deformation or yielding is observed to begin depends on the sensitivity of the strain measurement. With most materials, there is gradual transition from elastic to plastic behavior, and the point at which plastic deformation begins is difficult to define with precision. In tests of materials under axial loading, 3 criteria for the initiation of yielding have been used: the elastic limit, the proportional limit, and the yield strength. And on the figure 3.4, we can see typical tension stress strain curve for a ductile metal indicating yielding criteria. Point A is the elastic limit, is the proportional limit. Point B is yield strength or offset. 0 to C, yield strength. 0 is the intersection of the strain curve with a strain axis. The strain from point A to B and max case can cause a fracture. Okay. Now we got to mechanical properties on figure 3.6. The engineering stress strain diagram for soft polycrystalline copper. The low strain region is the A figure. Low strain region of initial linear elastic behavior followed by onset of plastic yielding, and the point B on figure B, the complete stress strain curve indicating the yield strength, tensile strength, and the present elongation to fracture. Engineering stress strain curve on various alloys are plotted in figure 3.7. As we can see, okay. It should be remembered that engineering stress is normally the nominal stress rather than true stress. In the initial portion of the plot, the amount of lateral construction of the specimen is distributed along the entire last strength. The specimen is therefore so small that the nominal and true stress are almost identical, not the same but identical. But in the latter portion of the test, necking of a tensile specimen occurs, that is, straining begins to concentrate near the region where the fracture will eventually occur. This necking can often be so pronounced that the nominal stress will decrease upon additional loading, as shown in figure 3.6b, the B figure, even though the true stress continues to increase until fracture occurs. Okay. we get to the figure 3.12 and 3.11. The three stages of creep curve and isochronous stress strain curve for specimen of a material creep tested at a given temperature. Okay. I got the creep deformation here. Creep deformation refers to time-dependent plastic deformation that occurs when a material is subjected to constant nominal stress. The rate of creep deformation depends not only on the magnitude of the applied stress, but also on time and temperature. Continuing creep deformation over time ultimately leads to creep rupture, also known as stress rupture. Now we got figure 3.13, the comparative fatigue curves. Comparative fatigue curve. The tendency of a material to break under condition of applied cyclic stresses is called fatigue. Fatigue fractures are different from the ductile fractures that usually result from regular tension and creep loading of most metals. Instead, fatigue fracture is caused by the propagation of cracks that initiate at a single point or at a viewpoint in the materials. And fatigue fractures are almost always brittle fractures. Most part and fatigue specimens contain point of stress concentration, such as surface roughness or a change in a part or specimen section at which stress is concentrated and where fatigue cracking initiates. The amount of concentration can be determined based on purely elastic behavior and is reported as the theoretical stress concentration factor or simply the stress concentration. And on figure 3.13, the toughness. The toughness also is the ability of a material to absorb an impact or shock load without fracturing. Specimen and notch geometry as well as the manner of law application are all important in toughness determination. For dynamic or high strain rate, loading condition, and when a notch is present, no toughness is assessed by using an impact test, such as Charpy impact test. That we can see, the amount of ductility is also related to toughness of a material. For the static or low strain rate situation, toughness can be determined from the result of a tensile stress strain test. It's related to the area under the stress strain curve up to the point of fracture figure 3.15. As we can see, the metal B is tougher than a metal A. Area under the stress strain curve as a measure of toughness. Okay, now we got to the point 3.2. Yeah, the strengthening mechanisms. Yeah. And I got two pictures here. Figure 3.15, a lot is distortion caused by solute addition, and figure 3.16, the back of alloying elements on yield strength of copper. Strengthening mechanism, the underlying structure of metal and alloys, be it macrostructure or microstructure, have an important bearings on their strength, ductility, and toughness. Strength of materials can be improved in various ways, as described in the following section. For example, a microstructure with finer grains typically result in both higher strength and superior toughness compared to the same alloy with basically larger grains. Other strengthening mechanisms are achieved at the expense of lower ductility and toughness. Thus, there may also be trade-offs between strength and ductility depending on the materials, the application, and the microstructural mechanism of strengthening. And the solid solution strengthening, as we can see in the figure 3.15 and 3.5 and 3.14. Oh, the 3.16, yeah, figure 3.16 is required to push the dislocation past the solute atom. The effect of several alloying elements on the yield strength on copper as shown in figure 3.16. Nickel and zinc atom are about the same size as copper atom, but beryllium and tin atoms are much different in size from copper at atoms. Increase in the atomic size difference and amount of allowing both result in increases in solid solution strengthening. Solid solution strengthening of iron and steel, addition of carbon to pure iron, and increased room temperature strength but more iron than 5 times. Yeah. And we got next the figure 3.16 3.18 figure 3.18 atomic size of a selected elements versus iron, with iron assigned an arbitrary diameter value of 1.0, elements within 15% of its size from 0.85 to 1.15 have a favorable size factor. For white substitution and solubility in a solid solution of it, those with a diameter to less than 0.59 have a high probability for intentional alloying with it. Okay, I think that's all of my presentation. Thank you very much.